This Friday will be the last class. Okay. Next week. Yeah, this Friday I can finish all the materials. So next week we don't have class. About the final exam. The final exam will not cover numerical linear algebra. That means, let me see, only the materials in the first book. That means in the notes covers a final exam. Okay, final exam covers lectures in the notes. Lecture 1 to lecture 31. Okay. Yeah. Doesn't cover numerical linear algebra. That means that cover this the sections or the lectures related to the homework problems. So how to review for the final exam? Same, okay. Review your homework assignments and take a look at the examples in the notes. What else? Okay. Yeah, that's it. Okay. Yeah.
Do we get equation sheets that we write?
Yeah, equation sheet. 10 pages on the both sides. Or if you want more, because in the midterm we allow 10 pages. Okay. I don't know if you want more, let me know. Okay, let me know. I just want to go through the notes. Okay. Don't print out the whole notes, too many pages. Yeah, Marco. Yeah. This Friday is the last class. Next week we don't have class. So I think I can finish all the materials by Friday. Today, still Jacobi method and how to improve Jacobi method. Okay, Gauss-Seidel. Okay. Take a review. Take a review. Marco, the final exam only cover is lecture 1 to lecture 31. Yeah, these lectures related to the homework assignments. Yeah. So no, it doesn't cover numerical linear algebra.
10 sheets.
10. Yeah, 10 formula sheets. Yeah. On the both sides, the same with the middle, with the midterm. Okay. Okay, take a review. We want to solve. Okay, solve a linear system. A coefficient matrix is large and sparse. Sparse, very important. Okay, sparse and large. The coefficient matrix. Okay. In section 4. Okay. In section 4, we consider iteration method of this form. Okay, which form? Yeah, this form. This form. T from coefficient matrix A. Usually T is sparse. What initial S any vector. Okay. K is from 0, 1, 2, and so on. So to run this iteration method, storage is cheap. Why it is cheap? we just need to store what? Store T. T usually sparse. T from matrix A. Okay. Yeah. Store T. Sparse matrix. And also store U, a vector. Also store C. That's it. Okay. So storage is very cheap. Okay. Don't use Gaussian elimination. Gaussian elimination. Okay. Storage very super expensive. This is cheap. Okay. Related to this scheme, we have a theorem. Okay. Yeah. Take a look. Okay. Here. Theorem. Okay. If the law of T is called iteration matrix. Less than 1, then guarantee. Okay. Let me give a name to this iteration scheme. Star. Okay. Then star will converge to some vector, say some vector u. Okay, some vector u. Here, I don't say that u is the solution of this linear system. I just converge to some vector u. You need to make sure this u is the solution of the linear system. For any starting vector, okay, for any starting vector, converge. And the error, okay, u k plus 1 minus u, okay, yeah, long less than equal to t, k, right? U0 minus u. Yeah. The convergence speed, how fast, depends on the log of t. Log of t less than 0 and close to 0, converge very fast. So it depends. Yeah. Okay. This is a sufficient condition. Okay. If this is true, then we have this. Now the following is sufficient and necessary condition, if and only if. Star converge, always converge to some vector u. Okay, for any starting vector, if and only if. Okay. Iteration matrix compute the eigenvalues of iteration matrix, then take absolute value on the eigenvalues. The largest absolute value is called spectral radius. Yeah, less than 1. In this case, we have u k. Here should be k. Okay, log k plus 1. Yeah. uk minus u long vector long roughly is equal to some number c times spectral radius to k times k to n. What is n? The size of the matrix. N is fixed. K changes. K is 0, 1, 2, and 3, and so on. Times log u0 minus u. What is c? Constant. C depends on u0 and the log that we chose. Okay, take a look. Then this is a review number one. Now review number two. What is Jacobi method? Okay, Jacobi method. What is Jacobi method? Let's see. Jacobi. Here, Jacobi. The Jacobi method. Expand the linear system into equations. For equation 1, solve the unknown x1. From equation 2, solve equation 2 for x2 and so on. Okay. In matrix form, okay, in matrix form, yeah. A split matrix A into L strictly lower triangular part, strictly doesn't include the diagonal. Okay, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, this is a matrix A. Matrix A. The strictly lower triangular part is this part. This part doesn't include the mid diagonal. And then plus diagonal matrix. Yeah, diagonal. And then plus U, strictly upper triangular part. Yeah, this part. Okay. Yeah, this part. Okay, this part. Yeah, this is U. Okay, U. Then plug this into the equation. Yeah. Then L D U is B. Okay. Now L U X plus D X is B. Move the first term to right side. Then we have D X B minus L U X. Now move D to the right side. Then we have X is U, D inverse B minus D inverse L plus U X. Right. Now, iteration method. How to decide an iteration method? Just up to you. It's up to you. Now, I decide the method in this way. Okay, I replace this X by U K plus 1, and then D, and then what? And then here minus D L plus U U K. Yeah. Then plus D inverse. Yeah, I design my method in this way. This is an iteration matrix T. This is a vector C. Vector C. An iteration method so defined is called Jacobi method. The Jacobi. Jacobi. And now we need to have a check, right? Check these conditions to make sure this method is convergent. In practice, matrix size usually is huge. Now, because computers are so powerful, matrix size are common, billion by billion, super large, and sparse. To compute all eigenvalues of a matrix, impossible. Okay, impossible. Maybe you need to wait for 1,000 years. Okay. Impossible. Billion by billion. Even though you get the eigenvalues, you don't trust those eigenvalues because of random error. Then impossible to compute this. Okay. Is there any way? Okay, before we use Jacobi method, we know the method, make sure the method is convergence. Okay, yeah, here is a fear, okay, fear about Jacobi. Jacobi, okay. Hey, fear, this is about Jacobi. About Jacobi, okay. Jacobi iteration scheme, okay, iteration scheme. Yeah, the scheme. If the coefficient matrix is strictly diagonally dominant. What it means? Okay. What it means? Yeah, we should say A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN. Yeah. A general matrix. Now we say that this matrix is diagonally dominant. That means diagonal entry A11, yeah. Absolute value A11 greater than the sum of S absolute values of the remaining entries on row 1. So A12 absolute value, A13, and so on. A1n. Okay, yeah. This is for row 1. For row 2, same. Okay. Diagonal entry A22 absolute value greater than the sum of the absolute values of the remaining entries on row 2. So this is A21 plus, okay, A22 on the left side. So A23 and A2n. Yeah. For a second row. For a third row, similarly, A33 absolute value greater than A31, A32, A33 on the left side, A34, and so on. A3n. This is the third row. The fourth row, same. Okay, so yeah. A matrix has this property, is called diagonally dominant. Now let me erase. Okay, now let me erase. If A is strictly diagonally dominant, okay, now conclusion. Then Jacobian, the associated, yeah, Jacobian iteration related to this matrix. Jacobi iteration will converge to some vector u, and that u is the solution of the linear system and converge to the solution x star of the linear system. Okay. Yeah, this film. Good. Okay, we don't need to compute eigenvalues. Yeah, just have a check whether a matrix is diagonally dominant. Yeah, have a check. Yeah. So here, let me show you. Say, take a look at one example. Yeah. One example. Yeah. Example. Okay. Example. 4x plus x2 plus x4 is 1. x1 for x2 x3 will converge to the solution of the linear system for any, actually, for any initial vector. Okay. Converge. And plus x5. So yeah, this is a linear system of 5 equations in 5 unknowns. Yeah. Now I want to apply Jacobi to solve this linear system. Okay. Okay. It turns out that the coefficient matrix is diagonally dominant. Yeah. Yeah. Coefficient matrix. Yeah. For 1, 0, 1, 0. 1, 4, 1, 0, 1. Then 0, 1, 4, 1, 0. 1, 0, 1, 4, 1. And then 0, 1, 0. This is okay. 0, 1, 0, 1, 4. Diagonally dominant because look at the first row. A11 greater than the sum of the remaining entries. A22 greater than the sum of the remaining entries. So this is a diagonally dominant. So therefore, when we apply Jacobi to solve this, any initial vector converge to the solution. Now, Second topic. What is Gauss-Seidel method? Okay. Try to improve Jacobi method. Gauss-Seidel. Okay, now let me erase. Topic number 2. Still section 9.4. Gauss-Seidel method. How to make an improvement on Jacobi method? Yeah, we need to know, recall Jacobi method. Yeah. A linear system, A11, x1, A12, x2, A13, x3, A1n, xn is B1. A21, A22, A23, A2n, B2. A31, A32, A33, A3n, B3, and so on. This is AN1, AN2, AN3, ANN, yeah, BN. Yeah. How to construct Jacobi? Okay. From the first equation, solve first equation for x1. Yeah. Then we get B1 A11 minus A12 x2 A13 A1n A11 xn. Solve the second equation for x2. Yeah. A21 A22 x1 and then minus A23 A22 x3 minus A2n A22 x. Third equation, right? Solve the third equation for x3. Then we get x3 is B3 A33 minus A31 A33 x1 minus A32 A33 x2. Low x3 because x3 is on the left side. So this is a A34 A33 x4 minus and so on. A3n A33 xn. All right. So yeah. Then replace the x on left side by u k plus 1, a vector. So this is should be u1, okay, the first component. Replace this by second component, okay, and this is a u3 k plus 1. The x on the right side, this is a u2 k, u3 k. This is a un k. Here, say u1 k, u3 k, un k, u1 k, u2 k, u4 k, un k, and so on to obtain Jacobi map. Now, questions? Now, Gauss-Seidel, okay? Iteration, okay? Iteration. After we are done with the first equation, we get u1 k plus 1. This is available. After we done with the first equation, this is available. Usually, the data in iteration k plus 1 is closer to the true solution, usually. When first equation is done, we have this available. Then use this in the second equation here. Right? Don't use UK1, but use U1 k plus 1. Yeah, this is available from the first equation. To compare U2 k plus 1. After the second equation is done, U1 k plus 1, U2 k plus 1 available. Now, use them in the computation of U3 k plus 1. That means that here, don't use this, okay? Use U1 k plus 1. Here, use U2 k plus 1 to compute U3 k plus 1. Do the same. For the fourth equation, now these three guys are available. Then use them in the fourth equation to get U4 k plus 1, and so on. That is Gauss-Seidel method. In matrix form, how to describe Gauss-Seidel in matrix form? In matrix form, derivation, okay, is very neat and simple, okay, in matrix form. Yeah, yes, matrix. Gauss-Seidel. Linear system, okay. Split matrix A as strictly lower triangular part plus diagonal part plus upper triangular part. Then plug this equation into linear system. Then L plus D plus U, X is B. X is B. Okay, now distribute X, okay. L plus D times X, U X is B, right? Is B, right? Right. Now move UX to the right hand side, okay? Negative UX plus B. Now move L plus D to the right hand side. Then we get negative L plus D inverse times U X plus L plus D inverse times B. Okay. Okay. Now I design my iteration scheme in this way. Replace this X by U K plus 1. Then the X on the right side by U K, and then plus L U L D inverse B. Yeah, I design this iteration scheme. Okay, yeah. 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 Iteration matrix is this. This is T. The vector C is this. C, vector C. Yeah. This scheme is called Gauss-Seidel. Okay. Yeah. This is a Gauss-Seidel. And now, electoral question is how to know Gauss-Seidel converge. Here is a theorem. Same condition with Jacobi. Yeah, with Jacobi. Theorem, okay, about Gauss-Seidel iteration. Same actually. If coefficient matrix A is strictly diagonally dominant. Yeah, what it means? Strictly diagonally dominant. Yeah, say this the following matrix diagonally dominant, but not strictly. Yeah, 2, 1, 1. 1, 3, 1. 1, 1, 4. Yeah, this matrix diagonally dominant, but not strictly. Why? Because look at the first row. A11 greater than or equal to A12 plus A13. Actually equal. Okay, not strictly greater than. Okay. So this matrix diagonally dominant, but not strictly. But how about this? Let me replace 3 by number. Replace 2 by number 3. Yeah. Now this matrix is strictly diagonally dominant because number 3 greater than. Okay, not equal. Okay. And then conclusion. Then the Gauss-Seidel ideal iteration will converge to some vector, and the vector is solution of the linear system. And converge to the solution of the linear system for any metric U zero. Electoral question is, I say that Gauss-Seidel is a improved version of Jacobi. Yeah. Is it true in practice? In general, in practice. In practice. Gauss-Seidel converge how fast? About about 30% fast. Okay, faster than Jacobi. In general. Say for example, if Jacobi solve a linear system, take 30 iterations. Say for example, then Gauss-Seidel usually take 20 iterations to converge. I have some examples on my notes. You can take a look at home. Next class, we present an improved version of Gauss-Seidel, and also I present Krylov subspace methods. Krylov subspace methods most popular. Krylov subspace methods are iteration methods, but higher level than methods in section 4. In methods in section 4 have some conditions to use. Say for example, matrix A strictly diagonally dominant. But many matrices, they don't satisfy this equation, this condition. Okay. We turn to Krylov subspace methods. So Friday, I present on how to improve Gauss-Seidel, then present Krylov subspace methods. Yeah. Okay, see you Friday. Yeah.